Have you ever gazed upon a star-studded sky and wondered about the fundamental nature of reality? What are the building blocks of our universe? Today, we embark on a journey into the heart of these mysteries, a journey into the captivating realm of quantum mechanics. The world of quantum mechanics is not easily grasped by our everyday senses. Imagine a single atom existing in two places at once, or a photon of light traveling along multiple paths simultaneously. When we attempt to measure the state of a quantum system, we force it to collapse from a superposition into a single, definite state. This inherent uncertainty is not a limitation of our instruments, but a fundamental principle governing the quantum world. Our journey into the quantum realm will take us through groundbreaking experiments that have challenged our understanding of reality. We will explore the famous double-slit experiment and Schrödinger's cat thought experiment, illustrating the concept of superposition. Fasten your seatbelts and prepare for a thrilling ride through the astonishing world of quantum mechanics. Our journey begins in the late 19th century, a time when classical physics reigned supreme. However, cracks began to appear in this seemingly perfect edifice. One such puzzle was blackbody radiation, the electromagnetic radiation emitted by an object that absorbs all incoming light. Classical physics predicted that the intensity of this radiation should increase infinitely at higher frequencies, a prediction known as the ultraviolet catastrophe. It was in this climate of intellectual ferment that a German physicist named Max Planck stepped onto the stage, forever altering the course of scientific history. Planck proposed that energy, unlike in classical physics, is not continuous but rather exists in discrete packets, or quanta. He suggested that the energy of each quantum is directly proportional to its frequency, a relationship captured by his famous equation, E equals h nu. Planck's constant, a tiny number with an enormous impact, would become a cornerstone of quantum mechanics. Planck's idea was initially met with skepticism. Little did he know that he had planted the seed of a revolution that would transform our understanding of the universe. In 1905, a young Albert Einstein published a series of groundbreaking papers that would revolutionize physics. Among these was his explanation of the photoelectric effect, a phenomenon that had baffled scientists for years. The photoelectric effect refers to the emission of electrons from a material when light shines on it. Einstein, drawing on Planck's quantum hypothesis, proposed a radical solution. He suggested that light itself is quantized, consisting of discrete packets of energy called photons. Einstein's explanation of the photoelectric effect provided further evidence for the quantization of energy, a concept that would become central to the development of quantum mechanics. As the 20th century progressed, more and more experimental evidence emerged supporting the quantum nature of the universe. In 1913, Niels Bohr proposed his model of the atom, in which electrons orbit the nucleus at specific energy levels. Bohr's model successfully explained the spectral lines of hydrogen, providing further confirmation of the quantum nature of the atom. In the 1920s, a new generation of physicists developed a more complete and mathematically rigorous formulation of quantum mechanics. Imagine a play on a grand stage, but instead of one story unfolding at a time, every possible scene, every possible line is happening concurrently. This, in essence, is the concept of superposition in quantum mechanics. Think of an electron, not as a tiny sphere orbiting the nucleus, but as a wave spread out across multiple possibilities. The act of observing collapses this superposition, forcing the particle to choose one state. The observer effect suggests that we are not merely passive spectators, but active participants in shaping the reality we observe. Let's introduce two new actors to our quantum stage, two particles that have interacted in a very particular way, becoming deeply connected, or entangled. Changing the state of one instantly influences the state of the other, as if they are communicating faster than the speed of light. This spooky action at a distance is one of the most bizarre and fascinating consequences of quantum mechanics. Entanglement is now at the forefront of quantum information science, fueling the development of powerful new technologies. For centuries, scientists debated whether light was a wave or a stream of particles. Quantum mechanics suggests it's both, depending on how you look at it. This wave-particle duality proposes that particles also exhibit wave-like properties. The dual nature of matter and energy challenges our classical intuition and suggests that the very act of observation influences the nature of reality itself. In the quantum world, certainty takes on a whole new meaning. Heisenberg's uncertainty principle states that we can never simultaneously know both the position and momentum of a particle with perfect accuracy. The more precisely we measure one, the less we know about the other. The uncertainty principle implies that there's an inherent fuzziness to reality at the subatomic level. It tells us that the universe is inherently probabilistic, not deterministic, challenging our classical notions of cause and effect. Our journey into the heart of quantum mechanics leads us to a deceptively simple experiment, the double-slit experiment. Imagine shining a beam of light through two closely spaced slits. Instead of two bands, we observe an interference pattern, a series of light and dark fringes. This is wave-like behavior, something we might expect from water ripples, but not necessarily from particles of light. Now, let's turn down the intensity of our light source until we're sending single photons, one at a time, through the slits. The interference pattern persists, building up one photon at a time, as if each photon is somehow interfering with itself. The double-slit experiment doesn't just work with light, it also works with matter particles like electrons. If we fire a beam of electrons at our double-slit setup, we again observe an interference pattern. This discovery led to the development of the concept of matter waves, a cornerstone of quantum mechanics. Just as light exhibits both wave-like and particle-like behavior, so too, it seems, does matter. We need to embrace the idea that electrons, and indeed all matter, possess an inherent wave-like nature. To illustrate the mind-bending implications of superposition, Erwin Schrödinger proposed a thought experiment in 1935. Imagine a cat sealed inside a box with a device that has a 50% chance of releasing a lethal poison within an hour. According to quantum mechanics, until we open the box and observe the cat, it exists in a superposition of states, both alive and dead. The act of observation forces the cat's state to collapse into one definitive outcome, either alive or dead. Until that observation occurs, the cat remains in a liminal state, a quantum limbo, defying our classical notions of reality. Section 1. Quantum leaps in technology. For much of its early history, quantum mechanics remained confined to the realm of theoretical physics, a strange and beautiful theory struggling to find its practical footing in the real world. But in recent decades, something extraordinary has happened. The once esoteric principles of quantum mechanics have begun to leap from the pages of scientific journals into the heart of cutting-edge technologies. This quantum revolution, still in its early stages, promises to reshape our world in profound ways. By harnessing the very principles that govern the behavior of atoms and photons, scientists and engineers are developing technologies with the potential to revolutionize everything from medicine and materials science to communication and computation. Imagine a world where computers can solve problems in seconds that would take classical computers billions of years, where unbreakable encryption protects our most sensitive data, and where new materials with unimaginable properties drive technological innovation. This is the promise of quantum technology, a field still in its infancy, but brimming with transformative potential. Quantum computing, reshaping the computational landscape. Quantum computers harness superposition and entanglement to perform calculations unimaginable for classical computers. Classical computers use bits, while quantum computers use qubits. Qubits can exist in a combination of 0 and 1 simultaneously, exploring many solutions at once. This makes them well-suited for complex problems like searching vast datasets or breaking encryption codes. Though still in early stages, quantum computing's potential is staggering. It could reshape the computational landscape, solving humanity's pressing challenges. In an age of ever-increasing cyber threats and data breaches, the need for secure communication has never been more critical. Fortunately, quantum mechanics offers a solution in the form of quantum cryptography, a revolutionary approach to encryption that leverages the principles of quantum mechanics to create virtually unbreakable codes. Imagine a communication system where the very act of eavesdropping would alter the message, instantly alerting the intended recipients to the breach. This is the promise of quantum key distribution, a technique that uses the properties of single photons to create encryption keys that are impossible to intercept without detection. Here's how it works. Imagine Alice wants to send a secret message to Bob. Using QKD, they first establish a shared secret key by sending photons encoded with random quantum states. Any attempt by an eavesdropper, Eve, to intercept these photons would inevitably disturb their delicate quantum states, alerting Alice and Bob to the intrusion. Quantum cryptography, with its promise of unbreakable encryption, has the potential to revolutionize cybersecurity, protecting our privacy and ensuring secure communication in an increasingly interconnected world. As we delve deeper into the quantum realm, we uncover a universe stranger and more wondrous than we could have imagined. The once esoteric principles of quantum mechanics are no longer confined to the halls of academia. They are driving a technological revolution that promises to reshape our world in profound ways. From quantum computers capable of cracking the codes of nature to quantum cryptography safeguarding our most sensitive data, the future is being written in the language of quantum mechanics. As we continue to explore this strange and beautiful realm, who knows what other wonders we will uncover? One thing is certain: a quantum future awaits, full of possibilities as limitless as the quantum world itself. Our exploration of quantum mechanics wouldn't be complete without hearing from the brilliant minds who have shaped our understanding of this extraordinary realm. These pioneers, driven by an insatiable curiosity to unravel the secrets of the universe, have gifted us with insights that continue to inspire and challenge us today. Niels Bohr, one of the founding fathers of quantum mechanics, famously said, "Anyone who is not shocked by quantum theory has not understood it." His words reflect the profound shift in thinking that quantum mechanics demands, a departure from our classical intuitions about the nature of reality. Albert Einstein, despite his reservations about some aspects of quantum mechanics, recognized its transformative power, stating, "It seems as though we must use sometimes the one theory and sometimes the other, and sometimes we may use either. We are faced with a new kind of difficulty. We have two contradictory pictures of reality. Separately, neither of them fully explains the phenomena of light, but together they do." As we stand on the cusp of a new quantum era, it's both exhilarating and humbling to contemplate the possibilities that lie ahead. The journey into the quantum realm has only just begun, and the discoveries yet to be made hold the potential to reshape our understanding of the universe. Imagine a world where quantum computers unlock the secrets of protein folding, leading to cures for currently intractable diseases. Envision a time when quantum communication networks span the globe, enabling instantaneous and secure transmission of information. These visions, once relegated to the realm of science fiction, are now within the reach of scientific exploration. The quantum revolution is here, poised to reshape our world in ways both profound and unexpected. As we conclude our journey into the heart of quantum mechanics, we stand at the precipice of the unknown, gazing at a horizon shimmering with possibility. The quantum world is rapidly becoming a tangible reality, shaping tomorrow's technologies. Each experiment and breakthrough reveals a universe more wondrous and mysterious. From the tiniest particles to the largest structures, quantum mechanics weaves a tapestry of interconnectedness, blurring the lines between observer and observed, between cause and effect. It's a realm where the impossible whispers possibilities, and the only certainty is the vastness of what we still don't know. The study of quantum mechanics is more than just science. It's a journey of the human spirit. It reminds us that the universe is full of surprises. Profound discoveries arise from challenging assumptions and embracing the unknown. Quantum mechanics will shape our world, enabling technologies like quantum computers and sensors. These technologies hold the potential to address humanity's pressing challenges. Quantum mechanics teaches us the universe is a dynamic web of possibilities. It invites us to embrace the mystery and marvel at its strangeness. If you enjoyed this deep dive into quantum mechanics, don't forget to subscribe, like, and share this video. Check out more of our content to continue exploring the wonders of the quantum realm.